Okay, so in this lecture, we are going to talk about the two square theorem. Okay, we are going to talk about the two square theorem, and let me first simply state the statement of the theorem. So, if P is prime of the form 4k plus 1, then P is a sum of two integer squares. Okay, so this is the question we would like to follow. Yeah, so now this statement has a completely algebraic proof, which requires notions of Gaussian primes, and simple primes and their correlations. And you can find a completely algebraic proof of this, I guess, in the book Algebra by Artin. I guess you'll find it here, or you might find it in Damit 40, which is the a completely algebraic version of the proof. In this lecture, we are concerned uh, about the geometric procedure to come up with the proof of this. Okay. Before proving this statement, we need a few prerequisites, sort of prerequisites. We need a few facts to talk about first. So we do that first, and then we will be diving into the proof of it. So these facts are to be established before moving on to the proof of it. So let me go through the facts one by one. Number one is that the multiplicative group of the field ZP is cyclic. Okay, and yeah, I guess I'll need only this single fact, but there are some sub facts which I'll come up as we go through the proof. So it's better I just present it as a lemma for the proof. Okay, the multiplicative group of the field ZP is cyclic. So let's start with the proof of this, and to prove this we need a small notion, which is just I'm adding it as a remark. For a group G, we define E of G to be the smallest positive integer k, such that G to the power k is equals to identity for all G in capital G. And obviously I'm talking about a multiplicative group G. Okay, so which is this is sort of immediate by definition. We know that provided any finite group, every element taken to the power of the order of the group is equal to identity. So immediately I can speak of the fact, immediately E of G is less than or equals to the order of G. Okay, okay, so I guess it's clear. We will require this to prove this lemma. So let's talk about the proof of the lemma. So let G be the multiplicative group of ZP, and let lambda be the with the value of e of g. I guess it's called the exponent of g. I just forgot the exact uh, statement, the word which this e of g represents. Whatever, but this implies that alpha to the power lambda is equals to e, or rather I should use 1 for all alpha in g. Right now, so this implies that alpha is a root of the polynomial x to the power lambda minus 1, but the x to the power lambda minus 1 has at most lambda roots, right? As x to the power lambda minus 1 has at most lambda roots, and we can see that all the elements of G are roots of s to the power lambda minus 1. Therefore, the total number of elements in G must be less than or equals to lambda, right? Because all the elements of the group G act as a root of this polynomial. So this implies that order of G is less than or equal to lambda, which is E of G, right? But we have already seen that E of G is less than or equals to the order of G immediate. It was an immediate fact. So this implies that E of G is equals to the order of G. Clear? So this is suppose I call it 1. Okay. Now to continue with the proof, we claim the following. We claim following: if G is a finite abelian group, then there exists an element such that the order of that element equals to the exponent of G. Now how will this exactly help us? Because we have already proved that the exponent of G equals the order of G. Therefore, if I find out an element whose order equals the order of G, then that element will generate the group G, and G will be just a cyclic group generated by this element small g. So we prove this statement. So to prove this statement, the only thing which we require is the fundamental theorem of finite abelian groups. So by the fundamental theorem of finite abelian groups, we have, so I can write G under isomorphism as a cross product of zd1 cross zd2 and so on till zds. Each of these are cyclic groups of order d1 d2 till ds, such that dj divides dk for all 1 less than equals to j less than k less than equals to s. So this is the procedure we follow. We talk about divisions, if you recall, right? Alright, so this comes out from the fundamental theorem of finite abelian groups. Now provided we have this, so then if small g is in capital G, then G to the power ds is equals to E, right? Okay, this follows from here, right? This follows from here, but this implies that the exponent of G is less than or equals to ds, right? Is less than or equals to ds, but G has a subgroup isomorphic to zds, right? So it is a subgroup isomorphic to zds. Okay, and if H is the generator of this subgroup, then by definition of a generator, the order of H must be equals to ds, but we know that order of H must be less than equals to the exponent of G in this case, because for that by definition the exponent of G is the value. See, H to the power the exponent of G will be 1, right? And we know that provide suppose an element has a given finite order, if that element raised to any other power equals 1, then the order must divide that element. In other words, that the order must be less than equals to that exponent, right? So so therefore the order of H must be less than equals to the exponent of G. but the order of h is nothing but ds, so ds must be less than or equals to the exponent of g, right, which will immediately speak of the fact that ds must be equals to the exponent of g, right, not h, sorry, it should be g, right. Clear? Got it? So yeah, so once we have proved this, thus there exists an element g in capital G such that the order of g equals the exponent of g, which equals the order of g, which implies that g is generated by the element small g. And this was the thing which we required. But how does this typically help us? So now let's see the proof. Okay, so now we come to the proof of the theorem. So the proof of the two square theorem, and the only thing which we will be using is the essential use of the Minkowski's theorem. Okay. So let's talk about it. So we already have established the fact that the multiplicative group G of the field ZP is cyclic, right, and has order P minus 1. But provided you start with a prime number, if you subtract 1 from that prime number, then that will surely be a multiple of 4. Okay, that will surely be a multiple of 4. Therefore, it contains an element u of order 4. But see, inside this group, the only element of order 2 is minus 1, right? But minus 1 is the only element of order 2 in G, right? Therefore, I need to have u square to be congruent to minus 1 modulo p. Clear? Now here is the trick we would follow. We would actually want to construct a lattice so that we can efficiently apply the Minkowski's theorem to it. And to construct that lattice, what we do is that, now let L in Z2 be a lattice consisting of the points AB such that B is congruent to U times A modulo P. Okay. Now you can efficiently follow it that therefore for each fixed A, B can take the values 0, 1 till P minus 1, which implies that the total number of cosets I would get out of this lattice L inside Z2 must be P, right? Or in other words, that Z2, the index of L in Z2 is exactly equals to P. But this implies that the volume of the fundamental domain for L is P. Now think about this statement a bit. Okay, think about this statement a bit. I hope you will get an answer that why the volume of the fundamental domain for L is P. Think about the fundamental domain to be the smallest fundamental structure with the help of which you can span out the whole of R2. Okay, or you can construct out the whole of R2. Think of it in that way. Okay, this is the only trick we would require, nothing else. Okay, therefore by so if you quickly recall that if you just go through the proof of the Minkowski's theorem now, you don't need to do anything else. Okay, then by Minkowski's theorem, you just need to construct a bounded symmetric closed space, right? Yeah, a bounded symmetric convex space uh, which would have a volume greater than 2 to the power 2 times the volume of the fundamental domain. In this case, in that case, we used to have, on a general note, we used to have 2 to the power n times the volume of the fundamental domain. Here we will have 2 to the power 2 times, because here n is equals to 2 specifically. Then by the Minkowski's theorem, any circle, center at origin, of radius r with area, so I have the area as pi r square and it should be greater than equals to 4p, contains a non-zero point of L, contains a non-zero point of L. Okay. So I can efficiently choose just r square to be 3p by 2. So this holds for r square to be chosen to be 3p by 2. Okay. Therefore, there exists a point AB in L which is not the origin, for which, now if it resides in L, and in fact it's since it resides in the circle we have chosen as the bounded symmetric convex space to implement the Minkowski's theorem, then I should have that a square plus b square, which is the norm of this point, or the distance of this point from origin, it is surely non-zero, because this point is not exactly the origin, and it should be less than or equals to r square. But r square is being chosen to be 3p by 2, which is less than 2p. Okay. But so to keep in mind that a square plus b square is less than 2p, but also that a square plus b square is nothing but a square plus u square a square, because I had chosen that b is congruent to so I should use congruent modulo p, congruent to ua modulo p, but this is congruent modulo p to a square times 1 plus u square. But we have seen that u square is congruent to minus 1 modulo p, which implies that u square plus 1 is congruent to 0 modulo p. So this is just congruent to 0 modulo p, which means that a square plus b square, firstly it is less than 2p, it is greater than 0, and is a multiple of p, right, because it's congruent to 0 modulo p, but the only multiple of p which is greater than 0 and less than 2p is just p itself. So this implies that a square plus b square is exactly equals to p. Okay. So that ends the proof of the two square theorem. In the next lecture we will be talking about the four square theorem. Okay. And the four square theorem is just sort of an extension of the two square theorem, where we find that every positive integer is a sum of 4 integer squares. Okay, that's exactly what we do. And to be just stated as an acknowledgement that the proof of this at least the two square theorem goes back to FERMAT. Okay. Where he stated it to Mersenne, I guess in the year 1640. Okay. The proof was, I guess, given by Euler. I don't exactly remember the year. Okay. Whatever. So let this lecture be up till this much. In the next lecture we will be talking about the four square theorem. So meet you guys in the next lecture.